Hello guys, welcome back to my channel SK's Physics, and today we will discuss about Physics class 12 chapter number 1, and our topic is applications of Gauss law. First we mention applications of Gauss law. First is to obtain field due to uniformly charged and infinitely long straight wire. Second, to obtain field due to uniformly charged infinite plane sheet. Third, to obtain field due to uniformly charged thin spherical shell. Field due to an infinitely long straight uniformly charged wire. Consider an infinitely long thin straight wire with uniform linear charge density lambda. The wire is an axis of symmetry. Suppose we take radial vector of O to P and rotate it around the wire. The points P, P dash, P double dash obtained are completely equivalent with respect to the charged wire. This implies that the electric field must have the same magnitude at these points. Your distance between O to P dash and O to P double dash also same. So the magnitude of electric field at these points are also same. The direction of electric field at every point must be radial. Outward if lambda is greater than 0, inward if lambda is less than 0. Here outward direction, that's lambda is greater than 0. Now consider a pair of line element P1 and P2 of the wire. The electric fields produced by the two elements of the pair when summed give a resultant electric field which is radial. Here consider line elements P1 and P2 and their electric field, and here the resultant electric field. And the total electric field is sum of that electric fields, which is also radial. Imagine a cylinder Gaussian surface which is minus infinite to plus infinite contain wire. Since electric field is everywhere radial, flux through the two ends of the cylindrical Gaussian surface is 0. Here everywhere radial. Now for two ends there is ds and E normal, so the electric field is 0. Electric flux is 0. At the cylindrical part of the surface is normal to surface at every point, and its magnitude is constant since it depends only on r. Here E and ds parallel. The surface area of the curved part is 2 pi rl, where L is the length of the cylinder. So total flux is equal to EDS cos 90 on A, EDS cos 90 on B, and EDS cos 0 on C. So it's only depend on C. EDS is equal to E multiplied by 2 pi RL. So flux through the Gaussian surface is equal to flux through the curved cylindrical part of the surface. Phi is equal to E cross S. Phi is equal to E cross 2 pi RL. The surface includes the charge equal to lambda L. Q is equal to lambda L because lambda is equal to Q by L. Gauss law gives phi is equal to Q by epsilon 0. Therefore, E multiplied by 2 pi RL is equal to lambda L upon epsilon 0 because Q is equal to lambda L. So, lambda L upon epsilon 0. Vector E at any point is given by vector E is equal to lambda upon 2 pi R epsilon 0 because LL cancel, lambda upon 2 pi R epsilon 0. So, vector E is equal to lambda upon 2 pi R epsilon 0 n cap, where n cap is radial unit vector in the plane normal to the wire passing through the point. Field due to charged infinite plane sheet. Let sigma be a uniform surface charge density of infinite plane sheet. We take x-axis normal to given plane. By symmetry, the electric field will not depend on y and z coordinates, and its direction at every point must be parallel to x direction. Your electric field will not depend on y or z coordinates. It's only parallel to x direction. We can take Gaussian surface to be rectangular parallel cube of the cross-sectional area A. Only the two faces 1 and 2 will contribute to the flux. Electric field lines are parallel to other faces, so they do not contribute to the total flux. Therefore, two faces that 2 multiplied by E ds, therefore 2E into pi r square. The unit vector normal to the surface 1 in minus x direction, while the unit vector on surface 2, that is plus x direction. Therefore, flux E dot delta S through both the surface are equal and that add up, so phi is equal to 2EA. Therefore, 2E into pi r square. The charge enclosed by the closed surface is Q is equal to sigma A is equal to sigma pi r square because sigma is equal to Q by A. Therefore, by Gauss law, phi is equal to Q by epsilon 0. Therefore, 2E multiplied by pi r square is equal to sigma pi r square by epsilon 0. So, E is equal to sigma upon 2 epsilon 0 implies vector E is equal to sigma upon 2 epsilon 0 n cap, where n cap is vector normal to plane and going away from it. Here plane sheet and the direction of electric field lines. Field due to uniformly charged thin spherical shell. Let sigma be a uniform surface charge density of thin spherical shell of radius r. First case, field outside the shell. Consider a point P outside the shell with radius vector small r. The electric field at each point of the Gaussian surface has the same magnitude. E is along the radius vector at each point. Thus, E and delta S at every point are parallel and flux through each element is E delta S because that's parallel. Summing overall delta S, the flux through the Gaussian surface is phi is equal to E cross 4 pi r square. The charge enclosed is Q is equal to sigma into 4 pi r square. By Gauss law, phi is equal to q by epsilon 0 implies E multiplied by 4 pi r square is equal to sigma upon epsilon 0 4 pi r square. Implies E is equal to sigma capital R square upon epsilon 0 small r square. Here q is equal to sigma upon 4 pi r square, so E is equal to q upon 4 pi r square epsilon 0. Vector E is equal to q upon 4 pi r square epsilon 0 into r cap. Here the direction is small r cap. Now for second case, field inside the shell. Consider a point P inside the shell with radius vector small r. The Gaussian surface is again a sphere through P centered at O. The flux through the Gaussian surface is E multiplied by 4 pi r square. In this case, the Gaussian surface encloses no charge because charge is only on the surface. The charge enclosed is q is equal to 0. Now by the Gauss law, phi is equal to q upon epsilon 0 is equal to 0 for E into 4 pi r square is equal to 0. So electric field is equal to 0. The electric field due to a uniformly charged thin spherical shell is 0 at all points inside the shell. Now you remember steps only to obtain field due to uniformly charged. First is flux, then second Q, and third, after applying Gauss law, find electric field. Here lambda L upon 2 pi r L, so E is equal to lambda upon 2 pi r epsilon 0. Sigma pi r square upon 2 pi r square, sigma upon 2 epsilon 0. Thank you for watching.